This double integral as a number you get in the end is the signed volume of this solid. Okay, so if this idea is driving through the double integral, we might be able to ask this question. For instance, if I want to ask what is the volume of the solid above the region R is equal to 0 between x between 0 and 1, y between 0 and 3 minus 3x, and below z is equal to 9x squared plus y squared. Okay, so for instance, you might see this kind of problem. They ask you the volume of a solid above a region in xy plane and below a surface. Z is equal to 9x squared plus y squared. What do you do? You're just doing the double integral on this region of this function. And then depending on what region you're getting here. So this region is y simple region. You have two numbers for x, two functions for y, and immediately you can do the double integral right here. So 3 minus 9x squared plus y squared dy dx. Okay, you can start doing the evaluation here. Okay. I'm going to skip the following steps because it's all single variable calculus. They're polynomials. You should have no problem in finding all the integrals. Okay. So you find the antiderivative for y, and then you evaluate against x. You get the volume, and this volume is indeed a positive value, right? Width in this region, 9x squared plus y squared is definitely above xy plane, right? I can also ask you the question: what is the volume of the solid on R and below another function, which is z is equal to 18 minus 9x squared minus y squared. Okay? So if I want to find the volume of the solid above this region, below this surface, what do? It seems to be a dumb question, but you're doing exactly the same thing. So you're taking the integral of R 18 minus 9x squared minus y squared and dA, and then you rewrite it in terms of y simple region. Okay. Now here is one additional question I want to ask. I want to find the volume of the solid still built upon this region and xy plane, but between these two surfaces, z is equal to 18 minus 9x squared minus y squared, and z is equal to 9x squared plus y squared. I want to find the volume between these two surfaces above the region R. Then you need to find the difference between these two regions, right? So if I want to find the volume between 18 minus 9x squared minus y squared and 9x squared plus y squared, then you need to find the difference between these two. The only problem is which one should I take the function as the subtraction? Which one is the one under it? You have to know which one is under, right? So this is 9x squared plus y squared. The other function is 18 minus 9x squared minus y squared. So a safest way you can do is to draw or sketch the surface and see which one is indeed in the below, which one is above, right? But you can also look at this region right here, okay? You can region is here, and you can take the difference. For instance, if I take the difference 9x squared minus plus y squared minus the other one, 18 minus 9x squared minus y squared. If I'm doing this, I can find several testing points in this region and see if that is positive or not. If it is positive, that is exactly saying this function is above, this function is below. Are you with me? I can test against a couple of points right here. For instance, if I pick a 0, 0, this function is 0, or this function is positive. Indeed, this function is in fact in the above. This function is below. So this function is actually below. This function is above. Again, I'm saying this is below, this is above only upon this region. Okay, so because this region is the interesting part right here, I'm only interested in within this restriction, which function is greater. Yep.
Well, there's like a region where it
Yeah,
intersects.
that's a very natural question. But in this case, it is designed this way. Within this region, one curve, one surface is always above. Okay. There are cases they will intersect and then will flip the rule. But in this case, on this region, I needed to take the difference between 18 minus 9x squared minus y squared minus 9x squared plus y squared and dk. So I need to take the difference between these two to find the volume. Okay. I'm subtracting this two because this function is in above and this function is below. Okay. So the thing I'm doing here is I use a test point here. And use a testing point, for instance, 0, 0. I find this is indeed not negative. So I'm sorry, this is not positive. So that's why I'm taking the other way around.
Then you only need one testing point, right?
You really just need a one testing point. Okay? But the safest way to decide or to see, verify if a surface is above the other one is to sketch the curve. Okay? So I want to end this section by mentioning one thing, area of a region. Okay? So area of a region is opposite with the idea of volume of a solid. When we have a solid in R3, we're talking about its volume. All right? When we have a region in R2, we can talk about its area. So area of a region can be evaluated by double integral. So area of a region is equal to the double integral of a constant function 1. So this is the formula here. For instance, if I have a region in xy plane R, I want to find the area of the region. The only thing I need to do is to evaluate a double integral with respect to a constant function 1. Okay, so this is the formula. You might ask, what the heck is this formula? Why I'm integrating against the 1? All right? I will give you one simple explanation, but you don't have to understand this. You have to remember this formula and how to apply it. So first of all, if I have an area of a region, if I have a region in xy plane, and I raise a solid with height equal 1, okay? So if this is height equal 1, and this is solid built upon this region in xy plane, so the volume of this solid will be exactly equal to, by using geometry, is equal to area of the region multiplied by the constant height 1. All right? You cannot use this geometric formula if your height is changing at different places. But if upon this region the height is always equal to 1, so the volume has to be equal to area multiplied by 1. Am I right? Are you with me? It has to be equal to area of the base multiplied by 1. So it's area of the base multiplied by 1. But the volume of this solid is exactly equal to, the volume of this region is exactly equal to the double integral of the surface defining function. What is the surface defining function here? Z equals 1, right? Z equals 1, because this is a height equal to 1, so this Z has to be equal to 1. So the area is exactly equal to double integral of a constant function 1 as the defining function for the surface, which is equal to the volume of the region, volume of the solid with height. Height equal to 1. Okay, so this is, you can call it a coincidence. This is saying the volume of a solid built upon a region with constant height 1 is exactly equal to the area. And because I know how to evaluate the volume, I will be able to know how to evaluate the area. Okay? Know with me? So for instance, if I want you to find the following thing. So I want to find the area of a region bounded by x equals 0, x equals 4, x equals y, and x equals, I think, so, and y is equal to 3x plus 2. Okay?
Should it be 1 for x?
Yeah, you can write it as y equals x. Doesn't really change too much because now we're really good at x simple and y simple regions. And so you can regard x and y interchangeably. So I have this area. I want to find the area of the region. This region is in xy plane. So using the formula, the area of the region is nothing but the double integral of the region with respect to 1. Right? So evaluating a double integral is always, the difficulty always lies in how to identify the region. Okay? So the actual evaluation is pretty straightforward, but I need to see where this region is and how can I identify it in terms of whether it's a rectangle, whether it's x simple or y simple, or it is a polar rectangle. We're going to talk about it in a minute. So x is equal to 0 is just a y axis. X is equal to 4, that's the vertical line at 4. So y is equal to x, that's a straight line passing through 0, 0 with slope 1. And this is a line passing through 0, 2 with slope 3. Okay? So this is y is equal to x. This is y is equal to 3x plus 2. Okay? Again, you don't have to be super precise, but at least you have to know which curve is above, which curve is below, which curve is left, which curve is right. That's the essential information you have to be able to extract from your graph, right? Other than that, you don't have to be super precise. So this is 2, this is 4, and the slope for this guy is equal to 3. The slope of this guy is equal to 1. The region is bounded by these 4 pieces, straight lines, has to be this region, right? Has to be this region. And I need to transform all this information into whether it is x simple or y simple. How do you want to identify this guy? It is a y simple region because x is bounded by 0, 4, y is bounded by a lower function and a upper function. So this guy is equal to from 0 to 4, from x to 3x plus 2, then 1 dy dx. Okay? Okay, and then you can simply evaluate and get a number here. Okay? So this number is going to be the area of the region. In fact, you can use elementary geometry to find the area. Right? You can use elementary geometry to find the area. However, calculus is much more powerful in terms of evaluating more general region. Right? So this one is a special region because their boundary are all straight lines. You can use elementary geometry. But in special cases, in general cases, you can have your boundary to be an arbitrary curve. You can still use this formula. Okay. Now the very last thing I want to say is I get a number. The area is in square unit. And the volume is in cube unit. That's the only thing I want to say. Okay, so for instance, if your unit is 1 feet, then volume is going to be cube feet, and area is going to be in square feet. That's where you go to buy everything. Questions about x simple and y simple regions? Right.
Could we evaluate that really quick? I want to check.
I think I did my work before, so the answer is equal to 24.
Yes.
Okay. So next, I see some other people raise their hands. Any other questions? So next, we're going to go beyond to talk about a polar coordinates. Okay. Which I am pretty happy to talk about this. So polar coordinates, if you really, after we finish the discussion of polar coordinates, you will feel pretty satisfied because it works so nice in some special regions. Okay? So the polar coordinate system involves r and theta. Okay? Again, our discussion on the double integrals is not only important by its own right, it is also super important in triple integral as well. So x simple and y simple region will come back again in triple integrals. This polar coordinate system will also come again in triple integrals. So we definitely have to be pretty smooth about it. R and theta. So theta is about the angle. R is about distance or radius, if you want, right? Is this how you learn about the polar coordinate system? So if I have a point in the plane, align this point with the origin, and this is the radius r, okay? And the angle between this ray and the positive direction of x-axis is going to be theta, okay? So within this class, let's fix our notation. R as the radius is always non-negative, okay? So we don't want to have the complexity coming from the negative radius. So you learned about the polar coordinate system before. You probably dealt with negative radius. But in this class, we don't need to deal with that. We can allow our theta to be negative. Okay, theta is to be negative is saying nothing but going clockwise, right? So if theta is positive, I'm rotating counterclockwise to get this rate. If theta is negative, I'm rotating the area around. So r, I want it to be always non-negative. Theta can be all real numbers. And also, we should be pretty comfortable about locating theta equals 0, pi half, pi, 3 pi halves, and 2 pi, right? And also minus pi half, minus pi, minus 3 pi, divided by 2, and minus 2 pi. So the angles should be pretty smooth around the whole globe right here, okay? So the relation between the polar coordinate system and a rectangular coordinate system is the following. X is equal to r cosine theta, y is equal to r sine theta. And also r is equal to square root of x squared plus y squared